Good morning, ladies and gentlemen. I hope that you can hear me. I would like to start this session by some introductory remarks. I would like to share the screen, if it's possible. Thierry, for me?
Yes, Ahmad, it's possible. You just have to share your screen. Partager l'écran avec la flèche verte en bas. Okay, can you see my screen now? Yeah, perfect.
Yes. Okay, so some introductory remarks about Piezotronics. What are the main challenges in this field in the light of the NEED project strategy? What we are interested in here is to study the new ferroelectric piezoelectric materials that, as you know, are used mainly for sensors and actuators, and hopefully more and more for nano electronics. These materials are part of the big family, the dielectric family of materials, and we can find piezoelectric, pyroelectric, and ferroelectric. Just to give a short idea about that, the piezo, pyro, and ferroelectrics are a family, a subfamily of the dielectrics that have the property of not having a center of symmetry in the crystal structure. And this confer some interesting properties for these materials. For example, for piezoelectric, it's material that can exhibit a voltage drop upon mechanical strain. So it can be used in sensors and actuators. Pyroelectric, it's now the heat that produces electric charge generation. And finally, the ferroelectric, which are materials that exhibit spontaneous and stable electrical polarization when electric field is applied, and it can be used in, for example, memory cells. These are family of materials that this is a family of materials that is very interesting for applications, but there are some challenges from the sustainability point of view. The main targets that are pursued in this NEED projects that we will be hearing next are first of all sustainable approach, mainly try to remove the hazardous materials from these structures, and mainly to work toward the replacement of lead, which is widely used in the PZT, the so-called this famous PZT materials. And also to focus on simplified and especially secured supplied chain for these critical materials, because some of the materials are critical, as in the same area as what we heard before. There is also another challenge, which is related to fabrication processes that should be more and more CMOS compatible. That means done on silicon substrate, but also to address the large surface applications, to implement devices using, for example, glass substrates. These processes have to be as well low cost and low temperature deposition processes. So these are some, introductory remarks about the strategy that is conducted in the NEED related Piezotronics projects. And we now can go to these projects and hear from the PhD students. So we have three presentations. The first from Ernesto Gisbertiolo on design methodology for sustainable IoT devices. The second will be given by Kwang-Chu Biu, a PhD student, development of Z and O thin films with controllable doping for their integration into piezoelectric devices on silicon. And finally, a presentation from Mohamed Bilal Hashimi, who works on the study of HZO films for MEMS applications. So I'll give the floor for Ernesto to start presenting his project. Ernesto, are you online? Can you take the stage?
Yes. Can everyone hear me?
Yeah.
Yes.
Okay. I think that I will share my screen with you.
Perhaps first, Ahmad, if you can unshare your screen.
I'm trying to do that really hard, but I can't.
Ah, tu y arrives. Attends, je vais voir si je peux le faire.
Okay, okay. Let's say the new share screen. I think I stopped.
C'est bon, j'ai stoppé. I have stopped your.
Okay, thank you. So Ernesto, it's up to you now, please. You have to.
Okay. Okay, can everyone here see my screen?
Yes, if you can put in a presentation mode.
Okay. Can everyone hear my see my screen?
Yes.
Okay, so let's get started. Hello, everybody. My name is Ernest Kisver, and I'm a PhD student working at the System Department of CLAT in collaboration with the CLAT and the University of Grenoble. My research
Ernesto, we only see your last slide, I think. Is there a problem with your presentation? Okay.
Yes, you're right.
Okay, thanks.
So my research focuses on developing a design methodology for sustainable IoT devices. The construction of this methodology is based on the inductive observation of two case studies, classified case study A and a commercial case study B. Now, the subject of my research arises regarding the significant increase of IoT devices in the last year. Statistics report that the number of connected objects overcome the number of humans by the first quarter of 2020. But unlike electronics, all these IoT devices don't work alone, but in collaboration with other edge devices and remote resources. So the main challenge and stakes of my research is anticipating and avoiding impacts related to the material and data flow of these IoT systems in order to make sustainable the Internet of Things industry. So the main question that led my research is how estimating the potential impacts of an IoT system and how reducing these impacts by a practical design methodology. A review of the related literature shows that this question is addressed partially in the context of wireless sensor networks or indirectly in the context of mechatronics. Specifically, few studies focusing on the eco-design of sensors only consider end devices for extending lifetime of wireless sensor networks, but without proposing improvements in their electronic composition. On the other hand, other studies exclude the edge and cloud resource from the performance design of mechatronics. Now, in general terms, there are no design methodologies proposing a global perspective that consider the sensing, the edge, and the cloud resource. So my main approach is to overcome these aspects by considering an IoT system as a three-layered architecture in which every layer has one or many devices. One device has one or many electronic components, and every electronic component performs one or many functions according to its capacities. The main idea is that data flows along this hierarchy. Now, the usual design procedure for IoT devices starts from a functional analysis of customer needs. Now, in this step, every function is dissected into sub-functions that will determine the specific electronic components of an IoT prototype. My design methodology suggests a previous optimization of in data manipulation in the sensing, edge, or cloud devices. Now, this optimization will disclose the appropriate alternatives of electronic components that must be later evaluated according to their physical and technical features and their potential environmental benefits. These aspects will later facilitate the identification of key parameters for launching fast life cycle assessment studies, applying design guidelines, and discriminate certain components. Now, if the global impact is not reduced, available modifications on such aspects should be applied according to an interdependency analysis of electronic components before the reevaluation of the customer needs. Now, data manipulation refers to the way by which an IoT system collects, processes, and sends meaningful data according to the user needs. Specifically, the type of raw data and the frequency by which this data is transformed into information and sent to the user interfaces. For example, if an IoT system aims to controlling the liquid level of an recipient, only electrical signals indicating specific content levels would be enough, contrary to an ultrasonic-based system, which may require accurate clocks to indicate the liquid level continuously. Now, notice that in the first system, the internal microcontroller's memory will be enough, while in the second system, saving data in an external memory will be needed. Now, in the context in my case study A, an autonomous sensing device based on an energy harvesting system stores 2 pairs of raw data types in an external memory. In this system, there is no data transformation in the sensing device, but in the edge device of the system, and a smartphone, which is in charge of collating data from the sensing the device's memory. Consequently, in my case study A, the selection of memory technology is critical, and different alternatives related to this component were evaluated using my design methodology. First, 3 different memory-based versions of the sensing device were evaluated on the basis of 3 of their material composition datasheets. Specifically, a ferroelectric RAM memory-based version, an OR flash memory, and an EEPROM memory versions were compared using an LCA software. Now, results show that in general, the ferroelectric RAM memory and the EEPROM memory versions have the most and the least impact respectively. Now, if we investigate the impacts of these 2 components individually, we can disclose some key parameters that explain these impacts. For example, the gold quantities in bound wires are crucial for all impacts, as you can see, especially in the mineral depletion category for the 2 memories, the ferroelectric RAM memory and the EEPROM memory. Also, when gold quantities are limited, in the case of the EEPROM memory, another substance such as silicon in dyes are critical for several categories, including global warming. Now, in addition to this, the presence of certain substance in integrated circuits has also significant impacts in specific categories. For example, in the case of the EEPROM memories, the presence of fluoroethylene increases the impact of the ozone depletion category, even in little quantities. Now, on the other hand, the technical features of electronic components may also help to apply design guidelines. For example, if we look for extending the lifetime of a device, we should identify the shortest life component that compromises this goal. Now, for memories, the writing cycles is determinant, especially for energy harvesting based systems, because data must be checkpointed continuously in memory to guarantee software continuity even every time energy available is depleted. Now, writing cycles of memories may be consumed rapidly if a program is complex, if the storage of raw data requires many variables, or if the energy available of the system is little. Now, although the writing cycles of ferroelectric memories are superior to the writing cycles of EEPROM memories, a ferroelectric memory-based version for my case study A will be over-designed, because the two pairs of raw data types that are collected are simple and they don't require checkpoints. In fact, the device's program uses the accumulated energy to store raw data directly to memory. And this memory content is transmitted to a smartphone whenever it is close enough to the transmission range of the sensing device. To conclude my case study A, I compare it with a similar system working with a single coil lithium battery, with the aim of determining key parameters in the evaluation of two different systems. Results showed that the energy harvesting based system is not combined. The energy harvesting system here represented in dark green is not convenient if its expected lifetime is equal to the lifetime of the battery based system, here represented by the light green color. If this system uses only one battery. Indeed, the impact of the additional components of the energy harvesting system, for example, capacitors, voltage detectors, and comparators, overcome the impacts of a simple battery-based system. But impacts of both systems almost equalize when the battery-based system uses 50 batteries along its lifetime. So in this case, expected lifetime parameter is a critical parameter for the environmental profile of the whole system of my case study A. Now, on the other hand, the analysis of data transmission frequency and the data generation rate of IoT systems would allow estimating and reducing the impact of cloud resource. For illustrate this idea, let me present my case study B, which is oriented to controlling water consumption. And it is composed of an inductive pulse emitter and flow controller and an internet relay. Now, in this image, you can see the distribution of electronic components of the system along all the functionalities of the IoT application. Now, the flow controller of this system plays an important role because it sends either summarized data to the internet relay every 15 minutes or raw data to the internet relay everywhere or whenever the user requests water consumption stats. Now, in the first case, the system generates less than a gigabyte of data in a year. Now, the necessary energy to transmit and process this data on the internet and on the cloud server produces only 4 grams of dioxide carbon in 1 year. However, this impact will rapidly increase if by a factor of 6 if the user consults water consumption stats on the cloud server, or by a factor of 25 if the user extends the network to its maximal capacities. Now, these aspects disclose 2 additional actions for the eco-design of similar systems. Firstly, designers should apply pre-processing routines in the edge site when raw data is simple. For example, in my case study B, we deal only with electrical signals. Secondly, designers should reduce the data transmission frequency or promote local computing in large sensor networks. For example, in my case study B, an internet relay can manage more than 55 flow controllers. 25 flow controllers. So the study of these 2 case studies lead me to some conclusions that I want to share with you. Firstly,
just so you know, Ernesto, you have 1 minute left. Thank you.
Okay. Firstly, significant impacts coming from the growth of IoT devices are expected in the next years if we preserve our current way to design the Internet of Things. And now, an IoT system is composed not only of sensing devices, but also of edge devices and cloud resources. This research proposed a design methodology covering this global architecture. And this methodology is based mainly on data manipulation along the sensing, edge, and cloud devices. Now, on the other hand, data manipulation determines the technological alternatives for developing IoT devices. Such alternatives must be evaluated in terms of their physical and technical features, in terms of their environmental performance. Now, my methodology gives the appropriate framework that helps designers to identify specific parameters for the sustainable design of their projects, or generic parameters that could be applied to different IoT systems. In this presentation, we identified some of these aspects in the context of memories. These parameters, together to other aspects, will be listed and published as an additional outcome of my research. Thank you very much for your attention, and if you have questions, I'm open to answer them.
Okay, thank you very much, Ernesto, for this exciting presentation on this systemic approach of the IoT system. There are some emerging concepts that are really very interesting in your talk. Maybe we can take one or two short questions from the chat. There is a question from Jean-Pierre Askin, who likes very much the first step in the case A study, I think. And he asks you, he invites you to think about the most appropriate technology that could be labeled low-tech to fill the requirements of the targeted application. This is your approach?
Yes, I think that it depends on data that will be treated. For example, if we talk about simple data, maybe it's more convenient to treat this data in the edge site. So in this case, we will use low-tech. For example, I mentioned that instead of using a very sophisticated ultrasonic system, we can use a very simple electrical signal-based system.
Okay, another last question, very short question from Thibaut P. How did you deal with the LCA of specific components, which is a hard task to practice, by using a commercial database or doing it by yourself? With material
I have a problem.
Yeah, can you hear us?
Could you repeat the question, please?
Yeah, it's the questions related to the LCA of specific components. How did you deal with it? Was it by using commercial? Using commercial databases, or doing it by yourself with material declarations? But if so, how do you deal with manufacturing process?
Okay, it's a very good question. I think that we have a main difficulty if we use material declaration datasheets. In fact, first we have an aspect that is a complete initiative of the industry. Some enterprises publish this information, and other enterprises don't publish this information. And for those enterprises that publish this information, maybe some quantities are hidden because these quantities represent the value proposition of this electronic component. So we'll deal with a confidential issue, but in any case, I think that for example, by measuring the dimensions and the physical aspects of some electronic components, we are a good idea of the impacts of these electronic components. For example, in the case of the quantities of silicon, we can measure, for example, the area of the dies, or maybe if the material declaration datasheet is not available. And another aspect is also the content of certain materials that have a great influence in the final impact of the electronic component. And finally, regarded, for example, in some life cycle assessment databases, we have the possibility of discriminate some electronic devices according to the packaging, to their packagings. So even if the information is not available, some aspects of these physical characteristics will be very useful.
Okay, thank you again, Ernesto. I understood that we're talking from Bolivia.
Mm-hmm.
Okay, thank you very much. It should be very early in the morning, so thank you again.
Don't worry. And just a little indication in the case of how can I conducted my research, for example, in the case of the memories. We know that we don't have specific electronic components, for example, in the case of memories of integrated circuits, but we can use another strategy. For example, take into account the material composition and try to modelize these electronic components in LCA software.
Okay, thank you again, Ernesto. I'm afraid that we have to move because we have to stick to the schedule. So now let me ask the next speaker, Kwang Chu Bui, to give us his presentation, please.
Okay. Hello, everyone. So today I would like to present to you my work, my thesis about development of zinc oxide thin film and nanowire on silicon with the control doping for the application in piezo device. So we know that the piezo material is the material that can convert directly the mechanical signal to electrical signal and vice versa. So it has many applications in many fields. And for nowadays, the most common material for piezo application is PZT because it had high piezo efficiency, but it's also containing lead, the very toxic and rare element. So people nowadays want to try to avoid this element and try to find another material that's more eco-friendly. And among of them, we have zinc oxide, which is the belong to the OXIDE structure. So thanks to that structure, it also have the piezo property. And also zinc oxide is the material that is abundant and biocompatible. So the motivation of my thesis is to try to develop the piezo device based on zinc oxide and try to improve its efficiency so that it can replace PZT in the future. In this field, there is a lot of interesting results from the past, and they managed to create the piezo-based device based on zinc oxide, like the nano generator, as you can see. And but the problem of the zinc oxide is the piezo efficiency is not high enough compared to the PZT. But this problem can be improved. We can improve the efficiency. The problem that make the zinc oxide have low piezo efficiency is because it have the screening effect. What is the screening effect? Is the because inside the zinc oxide structure there will be an unintentional other element, another dopant that we that is inside the, that's the after the fabrication we don't want, and it create the free electron inside the zinc oxide. And during the piezo in the piezo performance, the free electron can move freely to the positive polar, and which will reduce the piezo potential. So it means it will reduce the piezo efficiency. So to solve the problem, we need to reduce or to compensate the free electron. And in the other result, we have the simulation. They show that by reduce the electron free electron, we can significantly increase the piezo performance. As you can see here, we have the high dopant concentration, and when we compensate the free electron, we reduce this unintentional doping, and the piezo potential increase in nanowire and in thin film structure. So the objective of my thesis is I try to develop the zinc oxide. I use the method metal organic chemical vapor deposition, which is the method that can grow the zinc oxide very fast in large scale, that can be used in industry, and it also can achieve a very high quality. In my work, I will focus on investigate the growth condition, the temperature, the flow rate of the reaction, the growth time, the dopant, and the substrate. Try to analyze and understand the structural, electrical, and piezo property, and from that know how to improve the piezo efficiency. And also in the parallel, I also investigate other methods like annealing, plasma treatment after the growth to further improve the piezo efficiency. And after that, I also try to integrate the bottom electrode and top electrode to build the device. And also for the electrode, we also try to avoid use the toxic and rare element like platinum and indium. That's people usually use for the electrode. So to do that, I use the MOCVD system to grow the zinc oxide with the different parameter. And I analyze it by use the AFM, the atomic force microscope with the module piezo force microscope to measure the piezo signal. The system, in this system, what is do is we have the tip and is apply the voltage and AC voltage on the zinc oxide, and thanks to its piezo, it have the displacement, and this displacement can tell us the amplitude and the phase, which mean the coefficient and the polarity of the zinc oxide. And we also have the lithography to deposit the top electrode on the zinc oxide, and we use the transmission line measurement to evaluate the resistivity of the zinc oxide and the resistance of the interface between the top electrode and the zinc oxide. And also we have other crystal structure and electrical analysis. So here for the for some result, we see here that when I grow the zinc oxide with the different temperature, at 500 we get the zinc oxide with the thin film structure, and at 700 we have the nanowire structure. And we also see that by varying the other parameter like oxygen flow rate and dicing zinc flow rate, we have the thin film morphology change, and also the dimension like the diameter and the length of the nanowire also change with this parameter. So we see that there are different parameters, and it can affect on the structure, and also this will affect on the electrical property of the zinc oxide. And two of these will lead to the changing of the piezo property. So here what we see, what I want to show is I have the piezo formant on the zinc oxide on different morphology, the thin film, stack thin film, columnar thin film, and nanowire with the similar length and the same similar thickness and same length on the nanowire. We can see the topography from the AFM technique, and we have the amplitude of the displacement of the zinc oxide when we apply the voltage. And we see that when the thin film, from thin film to nanowire, the signal is brighter. It means the piezo signal or displacement is stronger, or the efficiency is higher. On the phase, what we saw is we see the polarity. For example, here the bright zone is the zinc polarity, and the dark zone is the oxygen polarity. We see that there are both polarity on thin film, but when it's changed to the nanowire, it have the more zinc oxide uniformity polarity. And we also, for the nanowire, because the nanowire have some gap between those nanowire, it's not a dense layer. So this signal is the noise, and actually the noise, because we fill those gaps with the PMA, one kind of polymer, so that to keep the scanning of the piezo in contact with the sample. And here we also see the histogram of this mapping. We see that the amplitude on the zinc oxide polarity from thin film to nanowire is shift to the higher value. And also we see that the signal on the oxygen polarity is the histogram is less on the nanowire, so it's more uniformity, and it's also, this means it's more favorable for the piezo application, because two opposite polarity can cancel out each other signal when we build the devices. Besides the performance, we also concerned about the economy of the growth process. From what I did, we use the growth condition. We can calculate the amount of zinc oxide we use during the growth process. And we also measure the dimension of the thin film and nanowire. And assuming we have the perfect single crystal zinc oxide, we can calculate the amount of zinc oxide that it deposits on the devices. And from that, we can calculate the efficiency of the growth process. We should notice here that the efficiency can be lower because I assuming the perfect is a perfect single crystal, but also the efficiency can, because in this calculation I use the 2-inch. Which is what I use in my experiment. But for the industry, when we increase the scale of the production, we can increase more fuel time for the efficiency. So for this, what in summary, what we have the thin film that grow at 500. And it gives us the very low growth, low efficiency, and low piezo. For the nanowire, we have a higher piezo performance, but we have to use higher temperature, so it uses more energy. But we have the faster growth, so we also reduce the time that we use for the energy. But modify the growth condition, we can improve both of them. We can, as you can see, in certain condition, we can improve the piezo performance and also maintain the economy of the growth process. And also for the we also try to integrate the piezo in the device, and we try to have the comparison with the zinc oxide grow on silicon highly doped and other electrode we use, for example, the ITO and AZO, which is common transparent electrode for optical application. And for my thesis, we try to avoid the indium, which is also a rare element, and we want to use the AZO, which is also the abundant element. And so you can see, because the bottom electrode is also the play a role on the substrate for the growth of zinc oxide, so it have an effect on the growth mechanism. So you can see here on the top view, with the different substrate, we have the different morphology. And because so the difference in structure is also affect on the piezo performance. And in the certain growth condition, we can also achieve the piezo amplitude higher and the more uniformity in the polarity on the AZO, which is the substrate that is more friendly for the environment. So for in summary, what until now we already investigate different parameters of the zinc oxide, and if give us many result, maybe possibility, so that we can improve the zinc oxide piezoelectric efficiency. And also the results show that the possibility to improve both the piezo performance and also the economy of the growth process. And when we integrate the zinc oxide with the AZO at the bottom electrode, the result also show that we can develop the zinc oxide based piezo device, which is eco-friendly and not limit with the piezo application. The result also show us that this device can also have a potential for other application field like optical and other electrical field. So thank you for attention.
Thank you very much for this presentation. maybe we have a short time for a very short question. Again, from Jean-Pierre Raskin, who's very active this morning. Thank you. So the question is related to the starting substrate for the Z-anode deposition. I think you have answered these questions. You used 3 types of substrate, I think.
Yeah.
Silicon, AZO, and Z-anode.
Yes.
Sorry, ITO.
ITO, yeah.
So the question, the next question is why you used MOCVD rather than reactive sputtering? This is one part. And what about the crystallinity of your Z-anode films right after MOCVD? Do you need to process annealing after deposition in order to crystallize in the desired crystallinity? Can you answer these questions?
Yeah, thanks your question. Yes. Okay. So we first we use the MOCVD system, the MOCVD method, because this can grow in the very large scale and very fast. As you can see here, we have the grow time is very fast. It's like 1 micron for for example here, like we have the growth rate is like 1 nanometer per second, so it's very fast compared to the other technique. And for the sputtering, I also read some paper and compared to my technique, and I see that most of people use grow the zinc oxide with the sputtering, and I think we achieve the crystallization in this method is better for the sputtering. But of course, for this technique, we need to analyze more to have the exact comparison. And for the other question you asked,
do you need to post-process?
Yes, actually for the result I show here, this is the ASCRO sample, no post-process, but I also have other process. As I mentioned, we have the post-annealing and plasma treatment, and in this investigation, we see that after the annealing, we even improve more the crystallinity of the zinc oxide, and thanks to that, the piezo even improve more. So we can combine the optimal of the grow process and also other post treatment to make the high piezo performance.
Okay, so I'm sorry, but we have to move forward because we are behind the schedule. So thank you again for this presentation. And let me ask the next speaker, Mohamed Bilal, to give his presentation, please. Mohamed Bilal, can you hear me?
Yes, I'm here.
Okay, so you can share your screen, please.
Do you see it?
Yeah, we can see your screen, but we can hardly hear you. So you can speak maybe a little bit louder.
Good morning, everyone. I'm Mohamed Bilal. I'm working on HAFNIUM, ZIRCONIUM oxide thin films for MEMS applications, microelectromechanical systems. I work between 2 labs, TIMA lab and LTM lab. I'm supervised by Professor Basrour from TIMA lab and Professor Sisi and Dr. Sam from LTM lab. So here's the plan of my presentation. A brief introduction to the ferroelectric materials, conventional materials, our material, HAFNIUM zirconium oxide, a brief comparison between them, and the advent of using single target sputtering, some main results, and conclusion. So, as Mr. TC said already, ferroelectricity is the ability of some materials of having the ability of spontaneous electrical polarization, which we can reverse by applying an external electric field. It has two electrical signatures, two peaks of current, or the famous hysteresis loop. And in terms of energies, the switching between two stable states of polarization. So every ferroelectric material is a ferroelectric one and piezoelectric one. We are targeting this property because every ferroelectric material is a piezoelectric one. And by targeting the ferroelectricity, we target a wider range of applications for the IoT ecosystem. So we can target for ferroelectricity, we can use it for the storage, and for piezoelectricity, we can use it for the data collection. So the conventional ferroelectrics, the first ferroelectric material was the Rochelle salt, discovered here in France, and actually the most conventional piezoelectric materials are the PZT lead zirconate titanate. So the category of hafnium zirconium oxide is a fluorite structure of ferroelectrics. This structure is simple. It's based on calcium and fluoride, and many oxides are based on this. Belong to this category. Among them, the hafnium oxide and zirconium oxide. We are working on both of them. The advantage of this category is that we can impact the properties by impacting the structure. So we can adopt this structure or allowing them to induce new properties. The advantage of using hafnium zirconium oxide is that this material is fully compatible with the CMOS process, and we can use silicon as a buffer layer, and it has a functionality as very small thicknesses around 10 nanometer and even less. And it exists already an industrial knowledge about both materials, hafnium oxide and zirconium oxide, because they have already been used as high-K dielectrics. So they won't need basic study for industrial integration. And another advantage is that France is the global leader of the hafnium production. Comparing to zirconium with other dopants of hafnium oxide is that hafnium is a byproduct of zirconium sand, and they have a very similar structure and the same chemical properties. And comparing to other dopants, the doping or alloying with zirconium gives the best ferroelectric properties comparing to the hafnium oxide doped with other materials, as we see in the figures here. And another advantage is the price of both materials are increasing since the interest in these materials is increasing. For the state of the art, for this material is started with the discovery of ferroelectricity in silicon doped hafnium oxide in 2011, and the number of hafnium oxide papers increased until the last year with 174 papers. And the main field, targeted field, is the ferroelectric for integration is the ferroelectric memories, and there are also other fields as the ferroelectric properties and piezoelectric properties. Comparing to other conventional ferroelectrics, the hafnium zirconium oxide have very interesting properties as very small thicknesses comparing to ferroelectric ceramics and PZT or even ferroelectric polymers. As comparison for one applications for ferroelectric memories, here we compare the hafnium zirconium oxide with PZT. It gives very interesting technical properties comparing to PZT, and even in terms of sustainability, using of the titanium nitride electrodes comparing to platinum is very sustainable. And PZT containing lead, which is prohibited in industrial since 2013. It gives a lot of advantage for hafnium zirconium oxide with a factor of 13 in thicknesses between hafnium zirconium oxide and lead zirconate titanate. For another applications, for the FEFET transistors, also the hafnium oxide based transistors give a lot of promise and properties comparing to the conventional materials. In this thesis, we use the sputtering techniques contrary to the most of papers which use the atomic layer deposition. Here we use the sputtering, which gives a higher deposition ratio comparing to the ALD. And another advantage in terms of sustainability, using sputtering comparing to the ALD is more environmental, and because the atomic layer deposition precursors are so chemical and are more harmful, gives more harm to the environment comparing to the sputtering targets. And here also we can have the whole stock with the electrode and the ferroelectric material in only one chamber. The main result is about the metal ferroelectric metal stack, and to optimize it, we have to study several factors, starting with the electrodes and the ideal range of temperature to induce the ferroelectricity, and optimizing the sputtered hafnium oxide thin films. First of all, we have optimized the sputtering of hafnium zirconium oxide by the sputtering technique. So the first thing is to confirm that we have kept the ratio between hafnium and zirconium oxide to 1. According to previous studies, the best ratio to have ferroelectricity in this film is the best ratio is 1. So we have used targets with the ratio of 1, and we are sure to have the same ratio for the deposited films. We have confirmed this by XPS, and we varied the several deposition techniques, and we assured that the deposition is stable. So we have optimized this. The second thing is that the ferroelectricity in hafnium zirconium oxide is limited to 25 nanometer. So here we started by depositing in the range below 25 nanometer, and we are sure that every time using the same conditions, we have the same thicknesses, as you see here by using the X-ray reflectivity and the FEVA-CM pictures. The second result is in literature the most used temperature for annealing is between 400 and 600. So we have conducted an in situ X-ray diffraction for higher temperature from the room temperature to 900 degrees Celsius. And here we have found that the operation of the structural signature of ferroelectricity by the apparition of the orthorhombic phase started below the 400 degrees, and it kept stable until the 900 degrees. So this result reflects the compatibility with the CMOS process of the background process. And even for cooling, we have always the orthorhombic phase. So we have always the orthorhombic phase comparing to other study where during the cooling phase, the orthorhombic phase disappeared. So from the range of 380 to 980, according to the statics also, we have chosen 4 temperatures from 500 to 650, and we have conducted the annealing during 1 minute under nitrogen atmosphere. And here we found the apparition of the orthorhombic phase at the 4 temperatures, and we have conducted the extract measurements, which gave the high hysteresis loop with relatively small values of remnant polarization that we are working on to optimize.
Thank you, Mohammed. Just so you know, you have 1 minute left.
Okay, thank you. Another factor is the effect of oxygen during the deposition. We have found it, and we have found the structural signature of electricity at 100 nanometer. This is the first, and we are optimizing it. And here are some results that confirm this finding. To summarize, the hafnium oxide, hafnium zirconium oxide has a lot of potential to replace the conventional ferroelectric materials for ferroelectric applications or piezoelectric ones, and the combination between hafnium and hafnium zirconium oxide and titanium nitride can lead to have transparent devices. And this is all. Thank you very much.
Thank you very much, Mohamed Bilal. So we have maybe time for a very short question again from Jean-Pierre. So he asks you to if you plan to use your azido layer as the electric gate stack for MOSFETs, and for getting a lower subthreshold slope than 60 millivolt per decade at room temperature. Do you use these layers in MOSFETs or just in MIM structures?
In fact, now the aim is to only to optimize the ferroelectricity and hafnium zirconium oxide to reach the maximum. For the application, we have for the ferroelectric properties, we don't have a precise application for it. But in papers, there are a lot of integration of ferroelectric hafnium zirconium oxide for MOSFETs, and they got threshold lower than 60. I think it was 44. It is a possible way that we integrate we use the hafnium zirconium oxide for it.
Okay, thank you again. Let's leave it there, and thank you for the presentation. I'd like to thank the 3 speakers of this session. We'll close this Piezotronics session, and I'll give back